Welcome. So in this video, I'm going to go over integration techniques for natural log of x and also for e to the x. So what I'd like to do is give you some strategies to approach problems so that maybe you've got an idea if something looks challenging or a little bit different, you've got these fallbacks to go to and always rely on. Okay, so I'm working out of the book on example 3, page 438, and this is part A, the first example they give you. So here's the strategy when you're looking at this. Notice that I have 3 to the x. I want you to start seeing numbers like 3 here or numbers like 5 over here in this example as being constants that can be pulled out of the integral. So the more you can understand like which part of this is more of the function itself and what part is the actual constant, what's just a constant number that's not changing, the better you get at understanding which is which, the more successful you're going to be at integrating. So anytime I see something like this with a constant, the number 3, I want to actually observe that as something like 3 times 1 over x. So this is the constant number, a constant multiple of this function 1 over x. And of course, based on our basic rules for integration, anytime I have a constant multiple like that, I can pull it out of the integral altogether. So this becomes 3 with the integral of 1 over x dx, like this. Okay, so now I can actually start thinking about what's the antiderivative for 1 over x. So thinking backwards, if I'm in the idea that like 1 over x is the derivative, what function would have given me that? Well, that's natural log of x. So the antiderivative for this is just going to be ln of x. We use the absolute value bars just because for the original function 1 over x, its domain is any real number but 0. But for natural log of x, its domain is only positive numbers, positive real numbers. So that's why we're using the absolute value bars here, just because their domains are technically different. So a number that I could plug in here is not necessarily going to work for natural log of x. That's why we use the absolute values. Okay, and then plus c, because I know there could have been this constant that when I take a derivative would not appear here, but it should be as part of that original function working backwards. We call that our constant of integration. Okay, so that one's done. All right, so with that same train of thought, that same technique of looking at problems is like which part is the function and which part is like a constant multiple of that function, let's use that idea here to deconstruct the function I'm looking at. So rather than see this as e to the x divided by 5, I want to identify my constant multiple and pull that 1 over 5 to the side over here. So this is actually 1/5 multiplied to the e to the x function. So notice here, 1 over 5, that's my constant. This is my constant multiple, the number part of it. This e to the x is the actual function part. Again, based on integration rules, I can pull that constant out in front of the integral. So this becomes 1 over 5, the integral of e to the x. And then, of course, we love the e to the x function because it is its own antiderivative, just as e to the x is its own derivative. So, right, they go back and forth without a lot of effort. This is going to look like 1 over 5 e to the x plus c. So technically, not a lot of work here. The original function that I started with is technically the same as the antiderivative, but the antiderivative has this possible plus c constant of integration that would disappear when you take the derivative of this back. We are now going to go over a handful more examples with some other techniques that are going to work for you. So continue thinking in terms of like which part is my function piece and what part is maybe a constant that I can pull out of the integral to make my life easier. So keep thinking in those kind of terms, but also use these techniques as you start integrating functions a bit more. Okay. So the first example looks like this one here, which if you're kind of observing in terms of derivatives and you're thinking back to, oh, how would I do this with a derivative? You might be thinking like, oh, I see an inner function here with an outer structure that looks like a square function. So you might be thinking like, is there some crazy chain rule thing that we have to do here? And the answer is not yet. So at some point we are going to be able to undo chain rule and do the antiderivative of chain rule, but we're not there yet. So instead we're going to use that technique kind of like we did with derivatives, where you just multiply everything out and then take the antiderivative of each little piece. So it's a little bit more work right now, but at some point we will undo chain rule. Okay, so in order to square this out, just multiply everything out, I'm going to use my kind of square the first, double the product, and then square the last. It's kind of an easy way for me to square things out in my head like that. And then we just take the antiderivative of each little piece of this function as we work across each term. So from here, notice that the only rule I really have to think about is power rule backwards. So power rule backwards, that's a matter of taking, well, if it's x to the n that I'm trying to integrate, then doing it backwards means raise your power by 1 and divide by the new. So increase by 1, divide by the new, something like that. And I personally prefer to keep that new that I've divided by as a fraction really out in front, because again, I'm putting a lot of attention to what is the numeric, like constant number portion of the term, and then what's kind of that function piece there, right? So I like to kind of delineate between the two. All right, so in this case, my exponent is 4 currently. So if I increase by 1, it becomes 5, and then divide by the new, that's a matter of 1/5. But I've got 4 multiplying to this thing altogether. So that 4 out in front ultimately just multiplies to the antiderivative, which is 1/5 x to the 5th power. Okay, let's keep going. Here I have an exponent of 2, so if I increase it by 1, I get 3, divide by the new, and I get that 1/3. But the constant out in front of that is going to be 12 here. And then for our last one, I love integrating constants, right? Because you just throw an x right next to it, and you have your plus c at the end, and then you're essentially done. We'll just do a little simplifying from here. So 4 times 1/5 is just 4/5 x to the 5th power. 12 divided by 3 is 4x to the 3rd power, plus 9x plus c. And then, of course, remember, you can take the derivative of this to check your work and make sure that you've done it correctly. But we can kind of see in our heads taking a derivative that, yeah, if I take the derivative of this, the 5 comes down in front and cancels with that 5, reduce the power by 1, and I get x to the 4th, and that is 4x to the 4th power. This one, if I take the derivative for this piece, the 3 comes down in front, multiplies to 4, drop the power by 1, and yeah, that is 12x squared, which is what I had started with. The derivative of 9x is just 9. Derivative of a constant, they go away, they disappear, it's a 0, so yes, I am getting that original function back. Okay, for this next one, you might run across a situation where you are dividing by the variable x, and so how do we handle that? Well, similar to like we did with derivatives, before learning quotient rule, you were directed to divide everything by an x. So use that same technique here to set yourself up for integration. If I divide everything by an x, then ultimately this just becomes 4x. I'll show you every little piece here. I'm ultimately just breaking up my fraction, dividing each piece by x. So it would look something like this. Yes. And now I'm going to go ahead and divide everything by x, simplify it down so that I can take an antiderivative just using power rule. Our next step would look like 4x, because that will cancel with one of those. These x's fully cancel, so it's plus 2. And then over here, remember to think in terms of what's the constant that I can bring to the front, and maybe what's the function piece. So this, I actually want to look at it as 3 times 1 over x dx. Okay, now let's begin taking our antiderivatives with each piece here. So the power currently on x is 1. I want to increase that power and then divide by that new power. And in fact, I'm going to just go ahead and I know it's going to be 4 divided by 2. I know that that number out in front, just like we did here with the 1/5 and the 4 became 4/5, I know that that's going to happen. It's going to divide my constant out in front. So this becomes 4 divided by 2. This one would just become 2x. 2 is a constant number, so we throw an x on the back of it when I take an antiderivative. And then here, my 1 over x, that's that really special function. It's natural log of x. So this part just becomes plus 3 times the natural log of absolute value of x, and then plus c right there. So that's our antiderivative for this one. Okay, in our very last problem, I have left us only a tiny bit of room, but that's fine because it's a lot more simple than it appears to be. So remember how natural log and e to the x are actually inverse functions of each other? When you're taking the natural log of e to some power, you're saying, hey, e to what power gives me this thing? Well, it's 4t. So it's going to be whatever exponent that is right there. Ultimately, this ln and the e cancel out, and what we're really doing is just taking the antiderivative of 4t dt. And just a super side note right here, notice that you're integrating with respect to t because there are t's in your integrand. So making sure that those variables match. You're just taking the antiderivative of 4t with respect to t, so those variables match anytime you're setting up your integral. Okay, based on our power rule backwards, I have to take the exponent, which currently is 1, increase by 1, divide by the new. 4 divided by 2 is just 2t squared plus c would technically be that antiderivative there, and then we're really done. And sorry, I just realized that this really should have gotten simplified down to just a 2. I'm sure that was bothering you really bad. Okay, so there's a few techniques for taking integrals at this level here. We don't have a ton of rules for antiderivatives yet, so it's important that you know how to rewrite every single equation in terms of just exponents like this by multiplying it out, or getting it to exponents by dividing, or even simplifying down the function itself so that really all you're using is that power rule backwards for antiderivatives.